Okay, so hi everybody. We're gonna look at our feedback we got for our PDR report when I was a senior in senior design for engineering. So overall, we were given a score of 75 out of 100. Okay, so C, not very good. We did pretty well in equality, conciseness, and effectiveness, 9 out of 10. Introduction, background, motivation, including this executive summary here, 14 out of 15, so we're very good. But we didn't do very well in the technical details. So communication effectiveness, and then the model assumption, 7 out of 10, or then sufficient discussion of results or conclusions, only 6 out of 10. And for our design and analysis, level of detail is only 6 out of 10. And then the correctness and completeness of the calculation is only 5 out of 10. So our technical analysis is pretty bad, pretty lacking, which is ironic because we're engineers. Project management, 12 out of 15 for budget, and then 16 out of 20 for schedule. So this is not too bad. But yeah, we definitely could have improved a lot in the technical area. So we were asked we were asked the specific details or takeaways from the report. So that's this part. Normally you have a concluding statement or something like that, but we didn't put that here. So you kind of leave the audience hanging or leave the reader hanging. Um, okay, so on the left, we put in like all the main technical questions. Some of them will overlap here. And as a team, I believe we met and then we talked about how we're going to answer these questions so that we can move forward. I'll come back to these questions later on. So for this question on page 4, let's skip the table of contents. We were asked, who has the autonomy? Isn't that a big deal? If you're buying commercially available autonomy, is that the electronics or aerodynamics? So here we said electronics and ground station, they're in charge of autonomy. Electronics, they own the Pixop flight controller, and then the ground station will handle autonomous functions. So just for some context, the Pixhawk flight controller, it's that black box that we saw before, this thing. Okay, let me go back to here. Okay, the next question we got is on page 5, next page. So if our professor was to understand this correctly, we have to demonstrate all the tasks that we're going to do in a safe manner at competition that we intend to do. And that's not what we said at the presentation. So we have to make sure that what we said and write matches correctly, it aligns. So besides demonstrating the basics for safety, we have to prove that the tasks you're going to do are shown in that video. Okay, let me see. The other question we're asked, what could trip you up at this point? If you're already shown in the video, you can do those tasks. What's going to stop you from going to compete? So we wrote here on this side, logistics. So if we forget to bring components or there's a shipping issue because we're going cross country from Hawaii all the way to Maryland, that's could be a delay in arriving any important equipment. And then if we don't have enough team members going to competition, that'll also be a big problem. I don't think we answered this question. Do you have to demonstrate safety? I guess as a team, when we had our meeting, for whatever reason, we didn't answer this question, which is kind of concerning because safety is extremely important. So I hopefully we answer that in a different meeting at the time. Okay, then on the next page, page 6, we had a typo here. This is objective. It should be threshold. Objective is when you get all the points. Threshold is when you only get half of them. Okay. So the next question we got is about waypoint navigation here. So on the left side, how does this waypoint stuff fit into the search area stuff? So we can clearly define the two primary tasks as separate tasks. They each have their own paragraph, as we said here. And we mentioned that, if you remember from before, we drew that picture. And I deleted it on accident, so I have to redraw it. So on slide 12 here, autonomous flight task or waypoint navigation, you start at some point A and you go fly to B and C and then so on and so forth. So for search area task, you have a bunch of waypoints along this lawnmower grid-like pattern. Okay, let me go back to here. Okay. And let's see what else we said. Can you be taking pictures while navigating the waypoints? So yeah, so you have to make sure everything's working properly during the waypoint navigation for that search area task. And you make sure the images work properly while you're doing waypoint navigation. So for here, let me just put this in the middle. So you would put waypoints so you can fly this grid-like blonde more pattern, but we made the camera take pictures every like 4 seconds or something. So it's independent of actually getting to each of those waypoints. So in other words, you don't take a picture at the waypoint. You just keep taking pictures every 4 seconds. Yeah. Okay, let's see. We did that one. And let's see what's next. These don't really add much information for the mission requirements. Okay, this is about the system requirements you wrote here. We just said you have to achieve all the stuff, blah, 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 for the autonomous and search area tasks. So in other words, every subsystem needs to do their part in these two tasks. And it's like, well, that's kind of obvious. We should elaborate a little bit more on that. So the system requirements, it needs more work. I don't think that question starts in here, but we should eliminate the system and subsystem requirements, replace it with function requirements. So like do mission statement, mission requirements, and functional requirements. Like we don't need both system and subsystem requirements. And our professor doesn't really see the need for system requirements. There's too many levels, and it's kind of a waste of time. Just here's all the requirements, then be done with it. That was his opinion. And then we should have mission operations be the requirement for the system requirements instead of just saying each subsystem will each contribute to those two tasks. Because mission ops is the highest and broad level of the project. So it's from like a system perspective. And that makes a lot of sense. Let's see, what else do we do? That one. Okay, speed. We saw that one over here. So page 9. Let's go to page 9. So we talk about speed. So how fast is our kit drone, fixed wing drone flying at that airplane? So speed refers to average speed during flight. Okay, so that's great, but we never gave a hard number, like 30 miles per hour, 40 miles per hour. That's super important because it's going to give you a time, how long it's going to take you to finish this grid-like pattern, right? We didn't do any of that. And so we need to know how this is going to affect all of this because if we're going to meet that proposed parallel line strategy. So we said higher speed, you get better. This is written poorly. Higher speed you have, the better. Okay, I don't know who wrote this, but when you're flying faster, you can cover more ground, right? But if your cameras don't work for some reason, you need more time to return and then fix it. And it's hard because we can't see the cameras working once it's flying. It's just taking pictures every 4 seconds. We don't have a way to see if it's working during flight. Besides speed, how much light is there? Yeah, that's a big question. And it's a big issue because it's a very dark day, then your shutter speed is going to be affected. If it's a bright sunny day, then, not too big of a problem. So that's also important. And I think that was this one. And then we also said that the altitude that you're flying at is an important factor because the faster you go, the more ground you can cover, but then the pictures might be blurry. If you fly higher, you could also fly slower, and then you can get more ground that way too. So there is a trade-off, but we didn't look at those specific details. And that's why we got docked on technical details and analysis. Okay, let's see, page 11. So again, here's the terrible DMM fixed wing drone comparison. And let's go to page 11. Okay, so this is a good example how we said the kits are not designed for competition and there's limitations for the Penguin that we bought. And it's fine. We can use it as a testing platform, see if it satisfies the needs of the competition. If it does not satisfy the needs of competition, or if it has significant problems, then you need another aircraft. I mean, it's kind of obvious, but what's important to know is that our professor doesn't want to have us adopt this buy, try attitude because we're not really like an engineer. So it's important you come up with a model, you test your model on the kit drone, does it match what your model said? If yes, then your model's good. If not, then you need to retune your model because some engineer already designed this kit drone, this penguin to fly. So that's important. And then when your models are correct, here this is the most important part. It gives you confidence in your next decision because your models are correct. We're pretty close to correct. And if your model is not, you have to reevaluate your models. And you don't want to have this buy and try attitude because you need to think like an engineer. So the main thing is we got to work on our models, incorporate the speed, the camera, the altitude, and determine what the drone needs to do instead of just saying kind of like an English paper status, like just do all this stuff. But yes, we need to be more quantitative about it. Okay, then the weight and balance analysis should be pretty straightforward. This is on page 12. Okay, it's this one. So here, do we mention it here? Let me see. Yeah, so you can have two scales, put the drone on top of that like this, and then you can help figure out the weight and balance. That way you can figure out where the CG of the aircraft is. CG meaning center of gravity, of course. If the CG is forward towards the nose, that's a better thing. If it's too far back, you get some pitch stability problems. Okay, let's see, page 4. Oh, wait, hold on. We already did this one. Page 12. Okay, so we'll talk about the battery stuff. Let me go there. The battery even lasts 30 minutes. So the old battery does. And the battery is the heaviest component, so you have to look at that as the first place to save weight. But we need to do analysis to look at what the minimum battery size you need, like what's the voltage you need, right? So that's important because that is going to tell you your design trade-offs. So it's important to look at that because if you have a smaller battery and if you just land several times, you swap with the battery, that affects your flight time. And then how does that affect your strategy? So then you have to consider the payload. So basically we said we need to test a new battery and we need to give a better explanation and analysis. Because again, we got docked heavily on technical details. Okay, let's see. So I don't know why I skipped that. Then what page is this? 12 still. So is your navigation team working in parallel, interdependent of the other teams? Okay, we have this on. So we're gonna say mission operations will handle the navigational side of things. And then we're gonna test waypoint navigation on our quadcopter drone. So we had another drone in the lab at the time, so we could do some testing there. But we should have kind of mentioned that here, or we also said you can just have another kit, another Penguin as the next best option. Okay, let's see, page 13. So here's the famous lift equation you can pull out of aerodynamics textbooks. It's like cool, but what does this mean? So how do we use this to improve your Penguin? How do you have the ability to affect any of these to increase your payload? Okay, so if you add a different motor prop combo and you get more lift, if not, you can have a second motor, one's pushing or pulling, whatever. If you got another motor, then you have to offset its own weight. Then you can increase battery capacity. So there's a lot of trade-offs here. So yes, we're going to try buy a bigger motor, and we actually did at the time. So that's how we're going to help us increase lift. Can you increase the area of the wings? We could, but we don't need to because we're going to try the bigger motor at the time. We talk a bit about the plan from area. That's the variable S here, for those who don't know. And is there any options there? Can you do a biplane? We said it's probably possible, but maybe not. Then we're also asking you add a flap or flaperon to change the CO. That's the coefficient of lift, the first term here. And what are the trade-offs? We said again, possible, but probably not. One of the reasons we keep saying possible, probably not, is because we're not super experienced in aerodynamics or airplane design, but we only know like the basics. We had a pilot on our team and he knew all this stuff. How did you decide this is the correct airfoil? Okay, so that's the next question here. So this graph here, we said it appears to be ISA 962, but we don't know the exact type, so we kind of just estimated it. So on airfoiltools.com, they show you the airfoil. It looks like a certain shape. And then we just kind of put the two side by side and say, yep, this looks close enough. And Okay, this is the CL alpha curve that we want. And CL alpha, this means coefficient of lift versus angle of attack. And let's see, we did that one. Okay, so page 14. So related to above, what suggests this? After close examination, its airfoil is an ISA 962 airfoil. This is a very subjective statement. And what we should have done, just take a picture of the airfoil from the Penguin and then show the ISA 962 airfoil and just put them side by side or overlay them. And that'll be a good way to say after a close examination, it is this type of airfoil. Okay, page 15. So let's see. Do we have it here? Yes, we put that here. Okay, so this is about the materials. So the Penguin has expanded polyolefin. And so the question here is, this is good that this material will work because it's used for drones. But our professor was wondering if you need to make any changes, modifications, can you bond to the material or can you machine it? So we said it's possible, but probably not, again, because we're not experienced in manufacturing and making new planes. Okay, let's see, page 16. If you have to make multiple landings for battery changes and the landings are manual, does that count as a manual takeover? So at the time, we're not planning to land again. We're just gonna take one battery, put on the drone, do everything, land, and then be done. That's it. But if we have to, you can if needed. Now, the other thing is if you have to do this strategy, land multiple times, we'll probably want to try to get Thomas landing to work. And then if that's true, then you don't need to worry about manual takeovers. So we need to ask David, our pilot, if this autonomous landing really counts as manual takeover, or if you have to land multiple times to change your battery, does that count as a manual takeover? And then 6.3.4.3 is the rule reference number from the competition rule book. Okay. The next one, how does this tolerance that you capture waypoints 50 plus or minus 50 feet accuracy, you need to maintain navigation plus or minus 150 or 100 feet along the flight path. Okay, so on the left here, so this is going to affect the picture overlap, right? So if you are like 100 feet on one pass, like too far left or too far right, like minus 100 feet on the other one, are you going to miss photographing a section? And then how does this accuracy rectify the navigation part, right? And are they connected? Because you might know where you are and the location targets or not, because maybe they're connected. So we don't take pictures at waypoints, as we said before. So we just take pictures every 4 seconds. So not necessarily at A, B, C, D, E, whatever. And let's see what else we write. So capturing the waypoints doesn't involve picture taking. So you intercept the waypoints in order, but you don't take pictures at the waypoint. It's every 4 seconds or something like that. Okay, let's see the next question. You should define navigational accuracy. Let's go to that one. Define navigational accuracy. I don't think we put it on the left here. Maybe we kind of put it here. Okay. Does the Pixar provide plus or minus 100 feet navigation accuracy? Guess we have it here. We don't know at the moment, and the GPS is a bigger concern. That's really, uh, yeah, this is related to the next question. So, does the Pixar do so independently, or do you need to provide it a GPS signal? If it has its own, how accurate is it? If it's not enough, it's not accurate. Can you provide an overriding signal so you get better accuracy? So the Pixar doesn't have a GPS internally, but it has the GPS attachment. And that one is plus or minus 20 feet. And I think, okay, that one's there. See the next question. If you switch gears to batteries and heading. Okay, this is switch gears to batteries. I'm not sure what this means. I forget the reason why Dr. Trimble mentioned this one to us. So I'm gonna have to skip the one. Sorry, guys. Okay, next one is your known payload chart above is in pounds, and then here this weight is in grams. So it's important you keep your units consistent. And then how did these values compare to your previous 1 pound battery estimate? Yeah, we didn't mention that here at all. It's good to put things into context and perspective. So generally, a reader doesn't owe you the time to do your unit conversions for you. So in case I did, and according to Google, 1.04 pounds is close to 470 grams. So 2 out of the 3 of these batteries actually don't meet your weight requirement. So these are all two. So 2 of these batteries are too heavy, in other words. So no good. I don't think we wrote it on the left side. Okay. The next comment. Okay, again, more things on batteries. So yes, the capacity will ultimately need to be determined this way, but you should be able to make an estimate. We don't have a model, okay? So again, we got docked heavily on technical details. So the theme of buy and try is going to get really expensive, especially if you don't have engineering analysis, right? So we got docked heavily on technical details. No model here, just if this works, great. If it doesn't work, buy something else. Like, no, you're an engineer. Think about it, come up with a model, make some predictions. Right, so here as engineers, we should be suggesting a model that characterizes what we want to know to the accuracy that it is useful, and then use the testing to verify the model and the decision based on the model. Okay, so that's the most important part. Because where are the models? We don't have one. Okay, that's why we got docked heavily on technical details. So this one here, um, oh this wait, where's this one? Okay, this one here. How can you meet the requirements when you haven't even defined the requirements? Uh, I think we didn't have any electronics requirements like how much capacity, voltage, discharge, and rate. So it's kind of unclear. How can you say that this Zippy battery is the one that you're going to select if you don't state your requirements and then you don't know if this is going to meet it or not? So from the port, cannot tell what capacity it needs to be because we never said how much capacity do you need, how much discharge do you need, how heavy should the battery be, what voltage do you need. All those things are missing. And that would feed it right into your requirements. But again, we didn't do that. So we got docked a lot of points. And let's see. Okay, so now we're on to speed controllers. So table 6 here. So ESC stands for electronic speed controller. This is the component that's in charge of sending current to the motors, and then the motors will spin faster or slower based on how much current is going to it. Okay, so some sign posting would be nice. So to like suggest or have like a small header to say like, okay, this is the ESC section, and then like somewhere over here, this is the battery section. Some sort of header that would be good to put. So same comment about weight. We got grams here, and then we mentioned pounds before. So keep everything either in pounds, everything in grams. Make it useful and easy for the readers and audience to follow. Okay, then we're on page 19. Okay, now we're talking about motors. So what was the thrust? Does that match what you would have predicted it to be from your research above when we did that static prop test? I would quickly try to find it. Okay, so here's the test that we had. So here's the picture, what we're talking about during the presentation. So does this static thrust test, does that model match the performance of that test? So then you have some confidence in your model for your thrust, and then you can answer analysis. And let's see, do you have room for improvement to fix your margin problem? Okay, so here we said that we performed a static thrust, right? We mounted downwards as we saw in that picture, and then we ran it for 30 minutes at half throttle, 50%. Okay, but it's a nonlinear voltage discharge rate, and then we couldn't simulate competition conditions. We have a severe problem here. Period, then lowercase found. Missing something, missing a subject here. So we should say like the team found that the battery motor can last for 30 minutes, and we expect to be flying for at least 30 minutes. The maximum time it takes for the motor to completely drain is unknown, so you have to do more testing. Okay, fine. And then there's some more components you need. But we don't actually mention any of the details of the static thrust test and how that relates to us knowing you're going to be able to fly for 30 minutes. And then what expected throttle are you going to be flying at for uh, these two these two tests? Let me go back to slide 12. So like, are you going to be going really fast to the waypoint navigation? Then that'd be higher than 50% throttle. Or are you going to take your time for search your task because you're taking pictures? You want to go a little bit slower. You don't want to get a blurry image, right? So putting that into perspective would also help too. But of course, we were young engineers. We wrote this more like an English paper. And so we got docked a lot of points again on the technical aspect of the grade. Okay. Let's see. This question is, I think this one is about, I think I skipped this one on accident. Yeah, so back on the batteries. So battery capacity determined this way. You need to make an estimate. Yeah, okay, let me backtrack on this one. So the models here, make a model based on the amp hours and the amps, and then you can try to get some like actual flight time. But this is not super accurate. You have to go do some tests, but then make sure your model looks pretty good. And then relate that to the throttle percentage as we said before for this part. Okay, so yeah, okay, we mentioned this one right about the requirements being satisfied for the battery. Yeah, so there are no competition requirements for the battery. So as long as you have a battery that's safe, then you're good to go. But our professors wants us to get into like the quantitative numbers and analysis and those kind of details for those requirements. Okay, and those are all the highlights that I think we compiled here. So there's more on the right, so I'll look at this one some more. So let's see. Let's go back down to see this one. Okay, it's good. It talks about some of the other warriors. But yeah, so you're still worried about our mathematical model. So like what is the model for thrust for the motor at 50%? How long is that going to last? What is the static thrust test for a motor if it's at 60% throttle? How long is that going to last? So things like that. Okay, then let's see this one. I don't see this in the above weight budget. So this is the Raspberry Pi onboard computer OPC. So we didn't put this in the weight budget. And so now our margin is totally blown. So if you remember, we had a chart about the payload. And let's see if I can find it. So the payload maximum capacity is 1.98 pounds. And then we had a table here, and our total at the time was 1.9. So we're cutting it really close. Again, 0.08 pounds of margin. That's not very good. That's way too small. But if you have this Raspberry Pi onboard computer that weighs a lot more than 0.08 pounds, so then our margin is completely blown. We're going to be flying with a much heavier payload capacity, and then that's no good. So page 20, let's see. Previous teams chose to do pictures at a rate of 2 frames per second. Okay. But we're asked, do you mean previous successful competition teams, like the first 5 places last year? It's not just any previous team, but the successful previous teams. That's a important distinction there. Okay. Okay, so here, this is where we get into some actual good technical analysis. So I'm just gonna quickly go through this. So if we were to have a picture frame rate of 2 frames per second, and if we have the same one in 25 minutes, if we take 3,000 pictures, um, let's see, then the worst case scenario, you can have the SD card, download all 3,000 pictures, and then we've got 15 minutes for image processing after you do your 30 minutes of flight. So you land, you got 15 minutes to process your images. And then after this, you have to go through 200 slides or 200 pictures per minute, find the targets, and then hopefully you can see them at a reasonable quality, hopefully with good resolution. And then the second option, you can constantly send pictures down to the ground station while you're flying. So it's like wirelessly. And then the drone can go around a second time for the lawnmower pattern. And then you can tell the team, okay, this target is kind of blurry or we didn't get an image here. You need to go back. And then the last option, you have that onboard computer, the OBC. We should have defined this acronym before it and the first time we mention it. And then the onboard computer does the filtering for you and then just sends the images that have targets in it. Those are the ones that we're interested in. Now that would simplify filtering further, of course, and then this system would improve image processing. But then doing this is kind of complex and difficult. So this paragraph is pretty good. So our professor, Dr. Trimble, told us finally some basic analysis on image and search strategy. This is much more, obviously much more is needed than this. But then does the 200 slides per minute also include downloading the pictures? The answer is no. This is just taking pictures. I think that's what we should have written. Okay, images will contain the targets and the weight. Yeah, so the weight is important because again, we're going to be over payload capacity if we include this onboard computer, as we said before. Okay, here we have a problem with spelling. We should put a space there. All right, so page 21, pilot needs, get this one. So if pilot needs to take over, can they see the plane well enough from the ground station to control it, or they need a heads-up display of some sort? So if you're just staring at this screen on the ground station, there's like a computer, and this is what you're looking at. Can you control the plane by just looking at this? That's what the question is asking. And I think you technically can, but it's hard because you can't get like an intuitive sense of where the plane's going. But you can see there'll be like a plane icon and it will be pointed in a certain direction so you can get a sense of its heading. Okay, let's see, page 22. Okay, this is kind of a silly thing that we wrote. This is not an issue because the team both operating systems. So we should say this is not an issue because the team has both operating systems. So we're missing a linking verb there, has. Okay, see, page 27. So I guess these pages were pretty good. And let's see. Okay, what is your strategy for finding a pilot? Will one of you be able to get up to speed on this in time, or do you need to find someone? Yeah, so we ended up getting two of our teammates up to speed. So they were our pilots. We had one guy, the main pilot, another guy was a backup. And that's a concern here because in the video, you have to show that safety pilot, and then he's the one flying the aircraft on his remote controller. And then you have to show him doing all these different things, flying for 5 minutes, doing a landing, doing a takeoff, climb, descent, turns, and all that. And so you have to show things like for 2 minutes and then a manual controlled landing at the end. So there's concerns if our team had the expertise to do that. And unfortunately, we had two people able to do that. Okay, let's see. The Pixhawk takes care of all of this manual override stuff for you, right? He, I think it depends on how you set up the controller, but generally, yeah. You can have like different modes and switches and flips for different things. Does the Pixhawk also do this? Flight termination systems. Yeah, there's a setting in Mission Planner that if you lose communication, then all this different things will happen. So if you lose communication for more than 30 seconds, you're going to automatically return to your takeoff location. If you don't have communication for more than 3 minutes, then you have a flight termination system, and then you follow the different protocol that's already provided for us. Okay, then this one. Does the Pixhawk also do? Okay, we just did that one. 20. So possibly to increase takeoff speed. That's your lift prone. Probably not, as you said, you have plenty of runway. So you can have a launcher if you want, but we probably don't need one. You can like pick up speed on the ground and fly like a conventional airplane on the runway. Like here, if you're on the far side, then you can just go fast and then you can ascend. We actually ended up throwing the plane and then like throwing the throttle up high and taking off that way. Okay, let's see. Of the aircraft. The batteries and at least 25% of the aircraft must be bright colors. We're missing the words of the aircraft there. Okay, page 29. The PDRs defining those things are not mutually exclusive. Okay, so we're talking about, let's see, the Gantt chart. That's project management stuff. Again, we'll make a video about Gantt charts a separate time. I'll do a tutorial on that later. When we look at fixed wing drone, manual takeoff landing, image processing, the research software packages, and then mission operations. So you create a first draft mission plan task. We are slightly behind schedule. We've been focusing on preparing for the PDR. So Professor Trimble is telling us the PDR is helping us define these things. So make sure that you're still on time. Like all the work that you're doing should be part of these milestones and big presentations and reports. And then probably higher based on the port. Yeah. The current payload is 1.9 pounds, but because we didn't include that onboard computer, it's going to be heavier than 1.9 pounds. Okay, let's see. What is your current estimated cost? We did not write that down. Yes, so that's a good question. Because looking for the bottom line here is looking for the cost here, not in appendix or conclusion. You have 18,000. You need 20,000. That's the difference. Is this hard or are there decision points? Can you take less people to get down to 18,000 if you don't find 2,000 more dollars anywhere? Yeah, we didn't at the time look at how much it costs per student to go to competition. So that would have helped a lot. Okay, this one, sentence fragment. The electronics and structural section was estimated using previous semester purchase order in conjunction with more kits the team may need. Yeah, it's a terribly written sentence. I'm not sure what we were saying. Um, the electronics and structural section. Okay, I think if I were to reword this, we'd say like we use previous purchase orders to estimate how many more kits we need to buy for electronics and the airframe. I think that's what we should have said. Okay, let's see. This, okay. So we originally wanted to purchase 3 drone kits, but shipping cost to Hawaii is high. So we ended up only purchasing 2. So this is a better lesson learned. This better be a lesson learned in your other purchasing estimates. So this is important as we buy more equipment and components. Okay, so conclusion. Okay, we did okay on that. So let's see. So for appendix, we need an actual column. Okay, so we have the total item cost but this is estimated. When we actually incorporate shipping, handling, other fees, tax, whatever, then that would be in the actual cost. So this is estimated. Okay, this one. Remember, the Boeing money can be used only for technical cost. So we cannot use Boeing money for the registration fee or travel at all, only for structural or electronics. Okay, so we look at our Gantt chart. So here, according to this Gantt chart, you're done with researching the camera, but you have no math or physics understanding the trade-offs. So I realize this isn't too much the MEs, the mechanical engineers part, the seniors, but it drives so many of your trade-offs. You need to include this information. Yeah. So at the time, let me move this out of the way. So this is this red vertical line here, and I'll explain this in the Gantt chart tutorial later on. This red vertical line represents the day in the project, and these black horizontal bars and the blue rectangles represent how much progress you've completed that task. So if you're on schedule, all the black lines should be right intersecting with that red vertical line, but they're not. We're on the left side, which means we're behind schedule. But when it comes to researching the camera, supposedly we finished this task in 8 days. So from 10:10 to 10:18, and then this is going to flow to research software packages. But this is incredibly important and critical because it affects a lot of our calculations, like image processing, how fast you're going, and then how much area on the ground can you cover, what altitude do you fly at, those kind of questions. And I think that's it. Yep. Okay, so overall, again, we got 75 out of 100. So some other high-level questions feeding off of knowing the camera specs. If you have a specific field of view, how much area can you cover? So we're gonna create a spreadsheet, which we did later on. And then what's the minimum square footage per pixel at a distance of blank? So if you're at an altitude of 70 feet, 100 feet, how much square footage can you get? So we can calculate this using our spreadsheet. If you know the size of the target, and then you measure the size of the pixel. So what's the pixel resolution required for a human to identify characteristics? So we can calculate this pretty easily. So if you look at pictures from 750 feet, take a picture of that target, you should be able to see it from 750 feet. So you can do some quick tests. At what point can we determine the five characteristics and when can we not determine them? So we know five characteristics when you're 300 feet above the target. And you cannot see three other characteristics when you're flying between 300 and 750 feet based on our physical limitations for our camera. So what's the optimal picture distance from target? So Steven, who was in charge of image processing, he was a subsystem leader. He said the field of view is 55 degrees for the Sony S1000. That's the camera that we bought. We can see with the naked eye two target characteristics at 700 feet. We can see the color of the letter and the shape. And then let's see, which do we program more, the ground station or the PixHawk? What's easier to program? So the PixHawk has a lot of code inside. It's kind of complicated to change. So we've done all of our tuning and mission parameter changing in the ground control station side. Okay, so those are the high-level questions that are related to this camera question and this last comment that Dr. Trimble mentioned, right? So all of these physics and math understanding from the camera affects all of these different questions. And I think we'd hit all of them right. Yeah. Okay, so that was our PDR report, and hopefully you will not repeat the mistakes that we made. And thanks for listening.